Pratibha, KL, is it visible slides? Hello?
Yes, sir.
Dinesh Kumar, are you there?
Yes, sir.
Okay, fine. So regarding the last topic, where were we? Any idea? Hello? Last class, we were dealing with demand paging. So as the name itself indicates, demand paging is nothing but on demand. The pages will be brought from the hard disk to the main memory. So no need to load the entire process. Suppose if the process is being divided into say 5 parts, no need to load all the 5 parts simultaneously into the RAM. So what we do is the required pages or the initial pages or the necessary pages, okay, so which are required to start or initiate the process, those pages will be loaded into the main memory, and the remaining pages will be kept in the hard disk. Okay, so upon the request or demand by the CPU, so for the pages, only those pages will be loaded into the main memory, and that we call it as demand paging. Okay, so like in demand paging also, we divide the process into equal blocks, equal parts known as pages, as well as physical memory is also divided into equal parts known as frames. Okay, like these sentences are similar to the paging concept. Okay, right. So the logical address consists of the page number and offset. Similarly, the physical address is consisting of the frame number and the offset. This we have seen, and we were discussing regarding the page table that will be used in the demand paging. Okay, so what are the various fields involved here? What are the various fields involved in the page table, which will be helping in the address translation as well as like in demand paging. So we make use of this page table. So we have here 1, 2, 3, 4, 5, 6 number of fields are there. So where this so first what I've written here, like all these rows will be indicating the page number. Okay, right? So for example, here I mentioned page 1. Okay, suppose if I'm referring to the page 1, so whether this page 1 is present in the main memory or not, that is indicated by which bit? Hello?
Valid bit.
Valid bit, exactly. So we can have the indication regarding the presence of the particular page. So for example, P1 page or P2 page or say P7 page. So whether the page is present in the main memory or not, that is indicated by the valid bit. And this like this bit can take only 2 values, like either 1 or 0. So 1 indicates that the page is present in the main memory, and 0 indicates that the page is not present in the main memory. In turn, suppose if the page is not present in the main memory, means where that page will be present? That will be present in the hard disk, exactly. So second field is the page frame. Okay, so this page frame field indicates here that so this particular page P1 is present in this frame 4 in the main memory. So where does these actual pages will be stored, in the physical memory or in the main memory or in the RAM? Okay, so that frame number will be indicated by the page frame field as shown here. Okay, and as an example, here I've taken the page 1. Okay, so this page 1 is present in the 4th frame in the main memory or in the RAM, or also called as physical memory. So regarding the protection bit, so the third field is protection bit. Okay, so this protection bit is this field contains the information for the page. Okay, so whether the page can be read from or written into the process. So we can have the protection like in terms of read protect, write protect, etc. Similar to a say simple Word file or a PDF. Okay, so we can have the control over the modification that can be done on the page, and as a user I can restrict any sort of modification. So for example, I can protect my file say from writing or from reading, etc. So exactly similar to that. So we have this protection information bit where we can protect like in terms of the reading, reading and writing aspects. Okay. So next field will be the reference information. So this information concerning the references made to the page while it is present in the physical memory. So suppose if this reference bit is set, okay, so this means that, this reference bit is set when you refer to any page either by read operation or by write operation. So this reference bit will be helping the operating system in page replacement algorithms. And like next we'll be seeing so many page replacement algorithms where we can have the replacement of one page by another page in the main memory. Like in those cases, like will be need of this reference information. So this reference information field, right, will be concerning about the references that are made to a particular page while the page is residing in the main memory. So next field is the modification bit. Okay, the modified bit or the modification bit field it is. So this modified bit is also called as the dirty bits. Okay, so this modification bit or the modified bit field indicates so whether the page has been modified while the page is in the main memory, right? Whether the bit is dirty or not. Okay, like when we call the bit is dirty, suppose if the page is been modified while the page is present in the main memory, like in that case I can call the page as a dirty. Okay, because the bit is a dirty bit. Okay, that is so when you write into a page, then this bit will be set to 1, right, by the hardware. Okay, suppose if you modify a page in the memory, so then it will be written back into the hard disk or into the secondary memory, and this bit is also called as a dirty bit. So it's called as dirty bit because it will be able to reflect the page state. Okay, so whether the bit is modified or not, that particular state will be indicated by the modified bit. And last field is the other information. So other information, like this field is concerned with the page example, like its position in the swap space. Okay, like other useful information with respect to the page will be highlighted in the other information field. So for example, its positions in the swap space. But again, the meaning of swap space, where this swap space will be present, this swap space is nothing but a small part of the hard disk. Okay, so where the other pages of the process will be stored. Okay, and this swap space will be containing up to date updated information regarding the process, means each and every page that is not present in the memory, all the information will be stored in the swap space, and this will be present in the hard disk. Okay, so the bottom line is like we'll be making use of this page table, like having these many fields. Okay, where the combination of the production information bit and reference bit and modification bit and other information, that will be called as the miscellaneous information. Along with that, we also have the page frame, where this field will be indicating the location, right, or in which frame, okay, the particular page is being stored, and a valid bit will be indicating that whether the particular page is present in the main memory or not. Okay, and like as I've shown here, this 1 or 0, 1 or 0, 1 or 0 means valid bit and production bit and modified bit can be either 1 or 0. Okay, so after this we have some important concept like that are related to demand paging. So while we're discussing the demand paging, like we'll be coming across these words. Okay, so for example, the page fault, and say page in operation, page out operation, and the word page replacement. Okay, so now let us understand the meaning of these words with respect to the implementation of demand paging. So what do you mean by the word page fault? Okay, so when the page fault will occur, okay, so so this page fault will be occurring, so when the required page is not present in the main memory. Okay, suppose if say CPU want to access page number 5, okay, and if that particular page number 5 is not available in the main memory, like in that case the CPU or the OS will indicate a page fault. Okay, so this page fault is nothing but an interrupt that will be generated by the operating system or the kernel to indicate that the required page is not available in the main memory or in the RAM. Okay, so to have the indication of this page fault, so what OS will do is OS will first have a check on the valid bit. Suppose if this valid bit is 1, means no problem, the particular page is present in the main memory and the CPU can access that particular page and it can execute. Okay, suppose if this valid bit is equal to 0, means that indicates that the required page is not present in the main memory. Okay, and the OS will be generating an interrupt so as to indicate a page fault. Okay, right. Second operation is the page in operation. So where this page in operation means copying the page from where to where it is. Can you see this?
Hard disk to main
disk,
memory.
yeah, hard disk to main memory. So for your like imagination, okay, so just recall this figure where we have the main memory or the RAM or the primary memory, and here we have the secondary storage device, also called as baking store device. And the best example for baking store device, secondary storage device is, what is that? What is this figure? A drum indicates hard disk.
Hard disk.
Yeah, hard disk. So with respect to this page in operation, what we are doing is we are bringing the process from hard disk to the main memory, and that we call it as page in operation. And what is page out operation means simply copying a process which is present in main memory, and that particular process will be copied from main memory to the hard disk. Okay, so you can easily understand by having the imagination of this particular figure, and also the directions are also indicated. Okay, so you can keep this as the reference point. Say from the main memory, if the process is leaving the main memory and going into the hard disk, means that refers to page out. And if the process is coming say from the hard disk and into the main memory, that we call it as page in operation. Okay, and regarding the page replacement, okay, so when we need to carry out the page replacement is needed if and only if the required page by the CPU is not present in the main memory. Okay, so when the allotted page frame are exhausted, okay, suppose if we have the occupying of all the page frames in the main memory by all the pages, means the, suppose if the main memory is full, okay, suppose if the let's say main memory frames are full, so then one of the page is removed from the memory and is replaced by the required page. So this operation is called as page fault. And this page fault, suppose if page fault has occurred, means then I have to go for the page replacement procedure. Okay, so the simple example to have this page replacement. Okay, so to have a better understanding of this page replacement, okay, like here I have drawn a simple diagram using which we can easily assume, okay, what will be going on like in case of a page replacement. Okay, say suppose if we have the hard disk here, and this hard disk has got how many pages? Page 1, page 2, page 3, page 4, like up to P10 pages are there. Okay, so suppose if our RAM is only having 3 frames, okay, F1, F2, F3, like what are these? These are the page frames, right, available in the RAM, and only we are made available with only 3 page frames. So but here we have P1 to P10, in total we have 10 number of pages. Okay, suppose if the CPU is requesting for page 1, means this page 1 can be moved from hard disk to the frame 1 of main memory. Okay, suppose if again CPU wants page 2, means again we can again we can move this page 2, say from hard disk to the frame 2 of main memory. Okay, and as we have here one more free frame, hence the P3 page can also be moved from hard disk to the main memory. Okay, so now the real case is occurring. Okay, suppose if the CPU is in need of the 4th page as well. Okay, so but in the RAM we have how many frames?
3.
Only 3 frames available. So then where to place this? No place is available, no space, no location, no frame, no block is available right in the main memory, so that I can place this P4. Why? Because we are being made available with only how many frames? 3 frames, and all the all the frames have been occupied by page 1, page 2, and page 3. Hence, for the movement of this P4 process, P4 page from hard disk to main memory, we don't have any empty frame. Okay, so then what to do now? How to place this P4 page in the main memory? I need to go for the removal of either P1 page or P2 page or P3 page. Okay, so by removing any one of the page, either P1 page or P2 page or P3 page, I can create one empty space for the new process, so-called P4 process. Okay, so that this new P4 page can be placed in the empty space created by removing any one of the pages. Agreed? Okay, so this we call it as page replacement, and this page replacement will be happening if and only if our RAM is full or the frames are fully occupied by the pages. Okay, and to have the storing of a new page, okay, no space is available. Hence, in that case, I'll be going for the page replacement, where I can replace any one page that is already present in the RAM by a new page. Okay, yeah. I hope this diagram is visible and understandable, right? So you can assume easily. Yeah. So now going to one more figure according to your book, which is discussing about demand paging and demand loading of pages. So what you can see here is, so we have the memory having how many pages are there? 0 to 7 number of locations are there, and we have here MMU. MMU stands for anybody?
Memory management
Memory
unit.
management unit, and we can also call it as ATU. ATU stands for address translation unit. Why? Because this particular block will be doing logical address conversion to the physical address conversion, and we have so one assisting or one helping data structure that we call it as page table. What this will do is, this will give the information regarding the valid bit. Suppose if the page is present, means that particular page bit is shown as 1. Okay, so we can have the indication regarding the availability of the page in the main memory, and second field is nothing but the page frame, and third field is the miscellaneous information. So this page table as a whole will be giving us information regarding the presence of the page in the memory, as well as which frame that particular page is present in the memory, etc. And we have something called as a free frame list. Okay, among the available frames in the main memory, okay, how many frames are free? That will be shown in the free frame list. And we have here something called as a virtual memory handler. Okay, so this virtual memory handler is nothing but a part of the operating system or a simple software that will be implementing the demand paging. And I hope we know the meaning of demand paging. So what is demand paging? Basically, on demand itself, okay, based upon the demand of the pages by the CPU, we can move the pages from hard disk to the main memory. Okay, right? If and only the CPU demands for a particular page, only that page will be loaded. Okay, not whole of not whole of the pages of a process will be loaded, right? Instead, what we do is only the required page will be loaded into the RAM. Okay, so that we can execute it, right? And this is nothing but the hard disk where we have reserved some space in the hard disk for the remaining pages of the process P2. Okay, so this swap space is nothing but some reserved area in the hard disk where we can store the pages of the process. Okay, so like in the logical memory, okay, suppose if I'm say doing the subtraction operation of an instruction present at the address 3,682, okay, 3,682. Again, we can have the separation of this address into two parts. Okay, so one is PI. So what is PI? PI is indicating the page number, and BI is indicating the byte count. Okay? Yeah, I mean byte count, or you can also call it as offset. Okay, so this address, this logical address will be considered as the higher bit becomes the page number, and the lower bits are representing the offset number. And this page number is indicating to which, I mean, this so-called page number 3 is stored in which frame before that. So whether this page number 3 is present in the main memory, how to identify that? By using the valid bit. And according to this figure, so this page 3 is not present in the main memory. Hence, it is having an entry of 0. Okay, so this page number 3 is not present in the main memory. Hence, its value is 0. And regarding the page 1 and 2, so this page 1 and 2 are available in the main memory. Hence, it is having an entry of 1. Okay, yeah. So we have an address of 3682, like that is generated by a CPU. Hence, we call this as a logical address that has got two fields, page number and the byte count. Okay, so like in this, what is the meaning of this is? So we first look at this page number 3, and as its value is equal to 0 means that indicates that the bit, I mean, like the page number 3 is not present in the main memory. Hence, its bit position is equal to 0. That indicates that P3 page is not available currently in the main memory. Hence, we have the occurrence of something called page fault. So the page fault will be generated as this page number 3 is having a valid bit of 0. That indicates that page is not presently in the main memory, and OS will be coming to know that the required page number 3 is not available in the main memory. So now, so this required page is now loaded into the RAM, okay, in one of the page frames in the main memory, okay, and that particular value will be updated in the page table. And as you can see that in the main memory, which frame is free? According to the entry in the list of free frames, which frame is free? Frame number 6 is free. Okay, so the second column of page table, the OS will enter the page frame number in which the required page is loaded. Okay, and the execution can be carried out. Okay, so let's assume this page number 6 is available in the main memory. Hence, the page number 6 is copied into the page table. Okay, so we need to update the page table, okay, so as to have the information regarding the availability of the page, as well as say what all pages are occupied and what all pages are free. Okay, yeah, so we can explain this information, right? So next is something called as virtual memory handler or virtual memory manager. So what we had seen here in the previous diagram, like which is a part of the operating system or a software which will be helping us in the demand paging. Okay, so this virtual memory handler will be taking care of the replacement of the pages. Suppose if the page is not available, okay, so then the required page will be taken from the swap space, okay, and the free frame available is identified, and in the under particular frame the required page will be stored, okay, and the same information will be updated in the page table. Okay, so now the same block has been explained here. So this virtual memory handler or virtual memory manager is a part of operating system or a software component of the virtual memory that will be able to implement demand paging. So the virtual memory manager will be using two kinds of data structures. So one is the page table, like what we have seen earlier, okay, as well as the list of free frames, okay. And information regarding all these fields are already been discussed for your information, okay. So suppose if in the examination, if they ask you to explain separately the virtual memory handler, so they can explain again the same page table and the free frame list and the meaning of virtual memory handler. okay, which is a software component, or it's part of operating system, which will be helping us to implement the demand paging. So you can explain the same fields like valid field, page frame field, and the protection bit information, reference information, like so whether the bit is been modified or not, like indicated by the modification field, and other information as such. So for your information, you can have the functioning of this virtual memory manager. So where the main function of virtual memory manager is to manage the LA space. LA stands for anybody? What is LA? Logical address space. Like so as to manage the logical address space, then implementation of memory protection. So then manage a physical memory. Physical memory means main memory, right? Or the RAM. Then allocation of physical memory, and to perform the page replacement. Okay. So like starting with this managing of logical address space means what? Okay, so this managing of logical address space means to set up a swap space of a process. Again, recall the meaning of a swap space. So a swap space is nothing but a small area reserved in the hard disk, okay, where we can store the uh, pages of a process. Okay, second function is to organize its logical address space in memory using page in and page out, and also maintain its page table. Okay, like all this operation will be coming under the management of logical address space. Then implementation of memory protection. So maintain required information needed for memory protection. So we can have the protection of a page against writing of a page or reading of a page, etc. So then manage physical memory means to keep track of occupied and free page frames in the memory. Okay, so we need to have an idea regarding the availability of free frames, means like in the whole bunch of frames of the physical memory. Okay, how many frames have been occupied, or how many frames are still empty, etc. Those information will be managed with respect to the physical memory. The fourth function is allocating the physical memory, means deciding how much memory is to be allocated to a process, and also revise this from time to time so as to meet the needs of the process and the operating system. Okay, so after each and every page replacement, I need to have the revision of all the information, okay, with respect to the say page, like the frames being occupied, like how many frames are free, etc. And last function is perform the page replacement. So perform the page replacement of a page when the page fault occurs. Like already according to the previous slide, we need to perform the page replacement if and only if a page fault is occurred. Okay, right? Supposing the required page is present in the RAM, means no need to do the page replacement. Okay, I repeat, page replacement is being done only when the page fault is being raised by the operating system. And a page fault simply indicates what? The required page is not present in the main memory. Okay, yeah, or all the frames are occupied, allocated to a process are occupied or not. Okay, right? So you can perform a page replacement, and that is one of the function of this virtual memory manager, what we had seen in this last figure. Here it is. Okay, so virtual memory handler manager. Okay. So a simple example has been given. Okay, so as to explain the page replacement. Okay, so we have the memory of a computer system consisting of how many page frames are there? 8 number of page frames are there. Okay, so once I say page frame, means that is with respect to the physical memory. Okay, so a process P1 consisting of 5 pages, a number from 0 to 4. Okay, so we have a process like by name P1. So this P1 has got how many pages? 5 pages, 0, 1, 2, 3, 4 pages. Okay, so only pages 1, 2, and 3 are there in the memory at the moment. Okay, like this figure is nothing but before the page replacement, you have the storing of page 1 in frame 2, page 2 is stored in page in frame 7, and page 3 is stored in frame 4. Okay, so the remaining page frames have been allocated to other process, and no free frames are left in the system. Okay, so So like once we have the page replacement to be done, means after the page replacement, okay, so what all modifications you can see here. So when compared to this figure and this figure, okay, suppose if you like see this page frame 2, okay, like earlier in the page frame 2 we had the storing of page number 1, okay, so but at the time T12 here, so process P1 gave rise to a page fault for page number 4, okay, hence here like if you look at the page number 4 here, so this page number 4 is now stored in which frame?
Second frame.
Yeah, second frame. And what about the second page and third page before it, I mean like before replacement and after replacement? Page number 2 and 3 have got no modification as such, only we have replaced this page number 4, okay, with I mean like into the page frame 2, okay. So now this page 1 is not available in the main memory. Why? Because its value is equal to 0, okay. So a simple example where we are updating the operation to be done right in the page table, right, is been shown here, okay. So can simply take this for example as an example. Like suppose we have like around two number of page replacement policies, namely first in first out page replacement policy as well as least recently used page replacement policies. Okay, so there along with the numerical values, right? Like we'll see the actual page replacement happening. So, but for now, you can simply take this as an example slide where we are showing the location of the page as well as like in which page frame they are present, and after the page replacement how the like how the page table will be updated. Okay, no need to worry much about this. Yeah, like as I said, so we have basically two number of page replacement policies algorithms according to your syllabus. So, but in reality, you can have n number of algorithms are available, namely FIFO, first in first out page replacement algorithm, and LRU. LRU stands for least recently used page replacement algorithm. Last one is optimal page replacement algorithm. For your syllabus, you don't have this. Okay, so this into mark, okay, this indicates that this is not there for your syllabus, hence no need to worry about it. Only we will be dealing with FIFO and LRU. And again, to explain regarding the page replacement, let's say when we'll be doing this page replacement algorithm, only when we have the page fault. Again, all these statements are known to you. Why? Because same figure was been dealt earlier also. Suppose if I have here P1 to P5 number of pages, and if the number of frames available are only 3, means these 3 frames can occupy how many pages? Anybody?
3 pages.
Suppose if in the RAM, okay, suppose if I have only 3 number of frames, means each frame can occupy 1 page. Hence here 3 frames can only occupy 3 pages. Suppose, yeah, suppose for the 4th page, suppose if our CPU is requesting for the 4th page, P4 means no space is available in the main memory so as to occupy the 4th page. Okay, hence what we should do is I should be able to replace any one of the page, right, available in the main memory, means like either I can replace this page 1 with page 4, or I can replace P2, or I can replace P3 with page 4. Okay, hence like here we have the page fault. So once page fault occurs, means I should be going for the page replacement algorithms, and namely we have first in first out and LRU. LRU stands for least recently used. Okay, so we have some principles based upon which I can replace any one of the page in the RAM with the required page. Okay, so this is the basic concept of this page replacement algorithms, and we have like as I said, so we have some principles, okay, or policies based upon which I can select any one of the page, right, in the main memory okay, with which I can replace this new page P4. Okay, yeah. So the policies in case of first in first out is you replace the page which has arrived first. Okay, like as the name indicates, first in first out. Okay, so the page which comes first will be able to get out of the queue first. Okay, so you can replace the page which has arrived first, or you select the oldest page as the victim page to replace. Right? Are you getting it? So according to this particular figure, okay, so the first page to occur is P1 page, and after P1, P2 has arrived. After P2, P3 has arrived. Hence, among these three pages, P1 was the first page to arrive. Hence, I'm supposed to replace P1 page, right, in the first in, first out algorithm. Means you replace the page which has arrived first. Okay, so you can have the better understanding of this once we discuss the algorithm. Okay, don't worry about much, right, about this. Only you can understand the meaning of each and every sentence, and the sentence meaning implication will be so well understood while we are discussing the actual problem. Okay, so but for now this FIFO, right, indicates that I need to replace which page. I need to replace the page which has arrived first, as the name itself indicates. Okay, second one is LRU. LRU stands for least recently used, means you replace that process that has not been used for a long time. Okay, so the unused page for a long time, which is still sitting in the main memory. Okay, so which is still wasting a large amount of space in the main memory. Okay, that particular page can be replaced under the least recently used. Okay, so for example, suppose if the requirement of the pages is say like first P1 comes, and like after P1 the next requirement is for P2, after P2 P3 is the third requirement, right? After P3 again P2 is requested, after P2 again P1 is requested, after P1 P4, after P4 P3 is requested. Okay, suppose if you say see the sequence of requirements, means nowhere you can find P5. Okay, so what I mean to say is like among these requirements, okay, so the least asked page is P5, hence I can go for the replacement of P5 process, I mean P5 page. Okay, right. So like in the next class, let me discuss with this first come first I mean first in first out operating principle, like along with the example. Still we have here 2 minutes. Okay, so the problem will be like in this way: find the number of page faults for the below given page reference strings. Okay, say these 3 2 1 3 etc are nothing but the given page strings. Okay, using which principle? First in first out policy, with the number of frames is equal to how much?
3.
3.
3, sir.
So this means what? We are made available with only 3 number of frames. F1, F2, F3 are the 3 available frames in which memory? Logical memory, not the physical memory na?
Logical memory.
No, in the physical memory. Yeah, frame refers to physical memory or the RAM. RAM slash physical memory slash main memory are the same. Okay. Yeah. So like say this 3 2 1 3 etc up to 1 3 4 are the number of pages that will be requested by the CPU, and all these pages will be present in the logical memory. Okay, right? So our process is been divided into 1 2 3 4 5 6, let's say like around 19 number of pages. Okay, so one single process is been divided into 19 number of pages, and all the pages will be stored in the logical memory, and I need to allocate each and every page from logical memory to the physical memory. And in the physical memory you have how many frames? Only 3 frames.
3.
Yeah. Okay, so by keeping this in mind, okay, how we can allocate these pages into these frames using which principle? First in first out policy. Okay, so